Now let's talk about how to determine the size of an earthquake. We have two measurements that describe the size of an earthquake, which are intensity and magnitude. Intensity is a measure of the degree of earthquake shaken at a given location based on the amount of damage. So in this case, when we talk about the intensity of an earthquake, we are looking around the damage, and then by judging from the damage, we identify the intensity of the earthquake. There is also magnitude, which actually is directly related to the amount of energy released at the source of the earthquake. So as you can imagine, magnitude is more of a scientific, more of a direct way to identify, to determine the size of an earthquake. So let's first talk about the intensity scales. We have this modified Mercalli intensity scale, which was developed using California buildings as its standard. So it works best for California. The drawback of this intensity scale is that the distraction may not be a true measure of the earthquake's actual severity because of the different rock types in the different areas of the earth. Also because of the different strengths of the buildings and building codes and all other parameters can affect the amount of destruction, not only the earthquake itself. However, let's learn a little more detail about this modified Mercalli intensity scale. It actually goes from 1 to 12. 1 is the smallest intensity and 12 is the largest one. So when we talk about the Mercalli intensity scale of 1 for an earthquake, that means the earthquake isn't going to be felt by anyone other than maybe being in special conditions, special circumstances. And when we go up towards 12, the way we feel the earthquake is going to be changing. And for the largest part, for the largest intensity for 12, the damage is going to be huge. And actually the waves are going to be seen on the ground surfaces like a wheat field that or like a sea surface. The waves are going to be actually moving the surface of the earth. And likely the human beings will lose their understanding of the horizontality. By looking intensity scales, we actually can create the intensity maps. So here you see the intensity map after Loma Prieta earthquake in 1989. And we have this red area, darkest red area with intensity of 8, which means it actually has the largest damage. And then the intensity decreases when we go further away from the epicenter of the earthquake. However, you see in this area, for example, the intensity gets larger compared to the surrounding area, even though it's further away from the source location of the earthquake. So likely in this area, because of the type of the rocks under the ground, the vibration from the earthquake was transmitted a little stronger than the area surrounding this place. So the damage was larger. Or it may be completely irrelevant to what's going on in the earth and the rock types, but just a poorly built buildings. So as you can see from this point, it is quite hard to use intensity scales as true scientific measures of the size of an earthquake. So instead, we have magnitude scales, which are more reliable for us. And the most common, most well-known magnitude scale is actually Richter magnitude. It is the concept introduced by Charles Richter in 1935. So the Richter scale itself is based on the amplitude of the largest seismic wave recorded, and it actually accounts for the decrease in wave amplitude with increased distance. So with the Richter scale, the largest magnitude which we could record on a Wood Anderson seismograph was 8.9, and magnitudes less than 2.0 are not felt by humans. Each unit of Richter magnitude increase corresponds to a tenfold increase in wave amplitude, which means between, say, 8.8 and 8.9, there will be 10 times larger energy release, or say 10 times larger wave amplitude going on. So we can just, at this point, I can actually emphasize that the energy release from the earthquakes compared to their magnitudes are going to be exponential. So we cannot just say that the energy release between 8.8 and 8.10 is going to be the same between, say, 2 and 2.1. Now let's just learn how to use this Richter scale for identifying the size of an earthquake. So here we have this seismogram recorded by a seismograph. First package, we have P waves. The second package, we have S waves. So what we do, we just look at the very first arrival of the P wave and then very first arrival of the S wave. And by looking at this distance in time between P and S wave arrivals, we determine the distance to the earthquake. And then in here on the left, we just put this 21st second, the distance to the earthquake epicenter on this graph, which actually lets us know about the actual distance in kilometers. Here it's about 200 kilometers away from where the seismogram recorded. And then we go for the largest amplitude we see on this seismogram, which is right in here. And then we measure that amplitude, which is 23 millimeter. So we go to here to the right side of the scale and mark 23 millimeter of this largest amplitude of the wave in here. And then we connect these 2 points with a straight line, while we are having the magnitude, Richter magnitude scale being in the middle of these 2 scales. And wherever our line crosses this Richter magnitude scale will actually give us the actual magnitude of this earthquake, which is around 5 in this case. So I just want to clarify here is that we call Richter magnitude, or we shorten Richter magnitude as ML. So here 5 shows the ML magnitude, Richter magnitude of the earthquake. Obviously, there are other types of magnitude scales. For example, moment magnitude, which is actually the most reliable one for us, which measures the total energy released during an earthquake. And we can calculate this moment magnitude by the average amount of slip on the fault, the area of the fault surface that slipped, and the strength of the faulted rock. So we have this equation, we need to put all these parameters in to calculate the moment magnitude. We also can calculate moment magnitude by modeling data from the seismographs. And we shorten moment magnitude as MW. So here you see a table showing the frequency and energy released by earthquakes of different magnitudes. So here you see around magnitude MW9, we average per year less than 1 earthquake with this magnitude. These are the largest ones that we could record. And there are 3 examples of these from Chile, Alaska, and Japan. The closest one was actually from Japan in 2011. And here you see the energy release in equivalent kilograms of explosives. And when we go down along the magnitude scale, we see this energy release is going to decrease by 32-fold. And between 8 and 9, we usually get 1 or so earthquake per year. These are quite great earthquakes. The closest one in here was from Sumatra, 2006. And then there are major earthquakes happening or getting the magnitudes between 7 and 8, which are around 15 per year. And here you see the examples of those. And between 6 and 7, we get average 134 earthquakes per year. And if you go down, you see the number of the earthquakes we are getting for these magnitudes increasing. That means we are having actually a lot of small magnitude earthquakes every year, which are helping to release the energy stored in those fault zones, which otherwise may lead to quite major earthquakes. And the energy released by these earthquakes when we go down in the magnitude scale decreases by 32-fold.